Let's return to our Jupyter exercise and use these two essential metrics to evaluate the quality of our transcript. To evaluate a transcript using WER and CER, we first need a reference transcript, often called the ground truth. The ground truth is the accurate, manually verified transcription of the audio content, which serves as the standard for comparison. In other words, the ground truth is the accurate text against which the transcription is assessed. It provides the benchmark for measuring the accuracy of the speech recognition system. WER and CER are calculated by comparing the errors in the obtained transcription against the ground truth. I'll assign the original text from the audio file to a new variable, which I'll name appropriately. You can find this text in the attached TXT file from the resource section of this lesson. I'll use triple quotation marks, which allow me to include the entire text block, even if it spans multiple lines or contains special characters. Great! Let's implement the essential speech recognition evaluation metrics in our code. In Python, the GWER library provides functions for calculating WER and CER. Using these functions is straightforward. Type WER and as arguments, place the ground truth and the variable in which we stored the transcribed text. Pass the result in a variable called Calculated WER. Let's do the same for CER and then print both results. Additionally, I'll format the output to show 4 digits after the decimal point. Let's execute and see what we'll obtain. The word error rate is 0.3390, meaning that about 40% of the words in the transcription are incorrect compared to the ground truth. That sounds like a lot. Let's break down why that is. The transcribed text contains several substitution errors with misrecognized words. For example, Ivan, which is my name, was written as YVONNE. I suppose that's fine, though I'm not thrilled about it. Let's see what else we can find. We observe that artificial intelligence was capitalized in the ground truth, but not in the transcript. These errors fall into the substitution category. The same goes for other transcript parts with no uppercase letters. Yes, the meaning remains identical even with these errors, but the specific words used are different, regardless of how slight those differences are. Furthermore, as we mentioned previously, the word term is used here instead of the correct turned. The same goes for machine learning in artificial intelligence, where the word in is wrongly used instead of the correct one, and. These substitutions alter the sentence's meaning or result in an interpretation that makes no sense. Overall, such errors significantly impact the WER because minor changes can quickly accumulate, particularly in shorter text where every word dramatically affects the total error rate. This emphasizes the importance of using accurate and context-appropriate speech-to-text algorithms. For example, models that incorporate punctuation are likely to handle capitalization better. Regarding punctuation, absent in the transcript, let's focus on another crucial metric, the character error rate. We see that CER is 0.0884, meaning that approximately 9% of the characters in the transcription are incorrect compared to the ground truth. CER considers each character individually, including punctuation, capitalization, and every distinct character in the text. And as we saw, there is no punctuation in the obtained transcript. Initially, you might think that, as opposed to WER, the CER result looks low, only 9%. But keep in mind that the ground truth has 471 characters, excluding spaces. This means that approximately 42 characters are wrong in the transcription, which is not a low number. CER is sensitive to all differences, including punctuation and capitalization, which are crucial for accurate representation and meaning in text. The key takeaway here is that our goal is to achieve lower WER and CER values. To do this, we can either process the audio file to improve the transcription tool's performance, or try a different tool to see if it yields better results. As you may recall, the audio file contains significant noise. So, what do you think? Would the model work better if we reduce the noise a bit? We'll try that in the upcoming lessons. To do that properly, we'll learn to visualize spectrograms, an essential tool for identifying a sound file's frequencies, patterns, and dominant noises. See you soon.